Welcome to this SOFICS video tutorial. In this video, we look at local ESD protection for analog IOs. Our society's demand for faster data transfer is always increasing. For example, with the recent COVID-19 pandemic, we saw an unprecedented increase in the demand for bandwidth for video calls and other content. This constant increase in demand is pushing the semiconductor industry to develop high-speed, wired, wireless, and other optical interfaces. IC designers who create high-speed interfaces cannot use conventional analog IOs. High-speed analog IOs require low leakage and ultra-low parasitic capacitance. Additionally, for applications like automotive, medical, or displays, there is a much higher ESD robustness required than the typical 2 kV HBM. Furthermore, the functional circuits, which are realized with tin oxide transistors in advanced FinFET processes, are very sensitive to ESD stress. The conventional approach for ESD protection in analog IOs is the dual diode approach. In this approach, we have one diode from the ground VSS to the IO pad, and a second diode from the IO pad to the power supply VDD. We also have a power rail clamp between VDD and VSS. The dual diode approach is very popular because it has a reasonably low leakage and parasitic capacitance, as well as a small silicon footprint. For situations where we have sensitive nodes, it is customary to add an isolating resistance between the IO pad and the functional circuit in order to increase the ESD design window. And for cases where the functional circuit cannot withstand any ESD current, then we typically add a secondary clamp behind the isolating resistance. This simple ESD protection scheme has several drawbacks. First, we have the isolating resistance, which can introduce a lot of noise and severely impact performance at high speeds. Second, we have the ESD diodes, which can introduce excessive parasitic capacitance between the IO pad and the power supply lines. Third, we have several applications where it is undesirable to have a diode between the IO pad and VDD. Think, for example, for the case where we do not want to couple noise from the IO pad to VDD, or for the situation where the signal voltage on the IO pad is actually higher than the VDD reference. A fourth disadvantage concerns sensitive nodes where it is possible for the voltage drop along the intended ESD current path, so that is along the diode, the bus resistance, and the power rail clamp, to be higher than the failure voltage of the functional circuit. One simple way of reducing the parasitic capacitance issue and improving the voltage tolerance is to use 2 or more diodes in series. However, this is seldom done because it would result in a higher voltage drop during ESD stress. The local clamp approach resolves all the issues of the dual diode approach by replacing all diodes with a single local clamp. The approach followed by SOFICS uses silicon-controlled rectifiers. Local clamps realized with silicon-controlled rectifiers have several benefits. First, we have a much reduced dependence on the bus resistance. Second, we have high-speed operation, which is enabled. For example, SOFICS has several examples where we really drastically reduce the parasitic capacitance. Third, we have a much lower voltage drop during ESD stress. And finally, we have the possibility to separately optimize the ESD protection for each IO. As we can see from the examples here, SOFICS has realized more than 100 custom local clamp solutions for clients. So feel free to get in touch with us to discuss about your own specific application. Thank you for following this video, and please stay tuned for the next ones in the series.